So good morning, everyone. Today we're going to be continuing our discussion on conduction heat transfer, finishing up what we've been looking at in terms of steady state heat transfer, and then moving on and seeing how far we can get in our discussion of transient heat conduction. So from last time, from our exploration on heat transfer by conduction, we had stated that in general, the heat transfer rate can be approximated by the thermal conductivity times the surface area of our object times the temperature gradient delta T over the material or the thickness of the object. And this was in general, we've been really looking at rectangular systems. However, we see slight variations in this when we look at cylindrical systems. And so when considering cylindrical systems, we find that our heat flux is going to be proportional to the thermal conductivity times our temperature gradient, but instead of in the dt dx direction, we're looking at the radial direction, where we find for that given system, the surface area is primarily described by 2 pi RL or pi dl, such that if we integrate this system, zero to Q, 0 to R, what we find is the generalized expression for a cylindrical system can be expressed as negative 2 pi L times K times our temperature gradient, delta T or TO minus TI, however you want to write it. But since we're looking at the radial direction, we find that instead of a thickness that we have to consider out, we look at the natural log comparison of the inner and outer radius. And if we wanted to, we can also consider this in terms of a thermal resistance system. Where the thermal resistance through a cylinder is going to be essentially ln of RO over R sub I divided by 2 pi Lk. So let's take a look at an example of using this expression. So consider a steel tube with a 60 millimeter outer diameter being insulated by adding to the outside of the tube a 50 millimeter layer of foam, which has a thermal conductivity of 0.055 watts per meter Kelvin, followed by a 40 millimeter layer of cord, which has a thermal conductivity of 0.05 watts per meter Kelvin. If the temperature on the outer surface of this pipe is approximately 150 degrees Celsius, and at the outer surface of the cork is 30 degrees Celsius, we need to determine the heat loss or the heat transfer rate through the insulating layers. So I'll go ahead and draw this up so you guys can get an idea of what I'm talking about. So in this example, I'm just going to call it heat loss through an insulated pipe. So what we have is a steel pipe And around that pipe, we have a layer of foam. And around that, we have a layer of cord. And I like to label these so you guys get an idea of what this looks like. So this is the steel pipe. Then we have our foam. And then we have our cord. The temperature here is approximately 150 degrees Celsius. The temperature here is approximately 30 degrees Celsius. We know that the thermal conductivity of the cord is 0.05 watts per meter Kelvin. The thermal conductivity of the foam is 0.055 watts per meter Kelvin. So in this system, we can find the heat transfer rate as delta T over R total, where delta T is simply 120 degrees C, and R total is R1 plus R2, or the thermal resistance through the foam and the thermal resistance through the cord. So the thermal resistance through the foam is ln RO over RI divided by 2 pi Lk. So the outer radius is going to be this distance here, which is half of the diameter of the steel pipe, or 30 millimeters, plus the thickness of the foam, which the thickness was given as 50 millimeters, or 110 millimeters. The inner radius is simply just the diameter or the length to get to the outside of the steel pipe, or 30 millimeters. Divided by 2 times pi. Now we didn't have an L, so for this problem we can take a basis, which the easiest thing to do is just say 1 square meter of pipe, or 1 meter for the length, excuse me. So our length will be 1 meter. The thermal conductivity of the foam was given as 0.055 watts per meter Kelvin. So if we run this calculation, let's see what we get. Oh, excuse me, that shouldn't be 110. Nobody caught on to that. That should be 30 plus 50, or 80. So I get a thermal resistance of approximately 2.84 kelvins per watt. So we can do the same thing looking at the cord resistance. And this would be ln of 40 plus the 80 millimeters, or 120 millimeters, over 80, divided by 2 pi Lk, or 2 pi 1 meter, times the thermal conductivity of the cord, which is 0.05 watts per meter Kelvin. So for this calculation, we're left with a value of approximately 1.29, which means our total thermal resistance is simply 2.84 plus 1.29, 4.13 kelvins per watt. Therefore, our heat transfer rate is going to be 120 degrees divided by 4.13 kelvins per watt. Or 29.1 watts. And then taking into consideration our basis per meter of pipe. Any questions on that example and illustration?
Dr. Lopez, I do have one question.
Go for it.
So when we assumed a basis of 1 square meter of pipe, does that always translate to a length, or no, basis of 1 meter of pipe, excuse me, I misread that.
No, I wrote it wrong originally.
Wait, so is the basis based on length or surface area?
It's based on the length. So I'm basically plugging it in here, or for L.
I see.
The pipe length wasn't given, so you solve for essentially the heat transfer rate per unit length.
Got it. Thank you.
Welcome.
Dr. Lopez, I have a question. When you're calculating QC, it's completely fine to have it just your temperature value as in Celsius and not converting it to Kelvin, even though. Okay.
Because a delta degree C is the same as a delta Kelvin.
Okay.
Because even if I convert 150 and 30 degrees to Kelvin, I'm adding 273 to both sides. But a good question. One last thing I do want to note in terms of heat transfer rates via cylinders is if I look at a system, let's say it's a pipe and I've got insulation here in blue. The insulation is going to reduce my heat transfer rate via conduction, right? Because I'm adding a thicker layer for heat transfer. However, what we find is, let's say if I add an even thicker layer, as shown by this dotted line, I'll essentially increase the thickness and the thermal resistance for my heat transfer via conduction. But what I find is that increasing the thickness of this insulating layer results in an increase in convection on the outer surface of the insulation, because I'm increasing the surface area of my insulation on the outside. And so simply putting, adding I'll make that even simpler. An additional insulation reduces heat transfer via conduction, but increases convective heat transfer. Which means there comes a point where adding additional insulation will actually hurt my system instead of help it. There'll be a point where adding an additional layer of insulation will result in an increase to heat transfer instead of a decrease. And so there exists what's known as a critical radius of insulation, where these two effects cancel. And simply put, the critical radius is equal to the thermal conductivity of your material over the heat transfer coefficient that exists on the outside of that material. So you're looking at a comparison between, I shouldn't say K sub m, we haven't used that ever. It's a comparison between the conduction through the material as well as the convection that occurs on the outside. This is an important thing to note. All right, now the last part of this steady state section discusses what's known as fins and fin surfaces. I don't like to get into them too much. You can read about them. They are really important and really useful. But what you have is essentially a system where you're creating additional surface for heat transfer and heat dissipation primarily. And what you look at and consider is the conduction from the base into the fin, as well as the convection that occurs from the fin to the surroundings. And at steady state, this Q convection equals the Q conduction, the Q convection equal each other, such that the conduction minus the convection equals 0. We can write a differential expression for this as looking at the differential along the surface as a function of the conduction that occurs minus the convection that occurs out of the fin I don't like that that keeps changing. And so we have conduction, convection. Now to solve this differential, it gets a little confusing, primarily because the solution involves hyperbolic functions. But what I can state is that for most often than not, what we're typically concerned with is the fin efficiency, or how well is the fin operating, which the efficiency is going to be a function of the heat transfer rate of the fin over what's known as the maximum heat transfer rate that can exist in the fin. Where depending on the fin you consider, if the fin is long or is considered adiabatic at the tip, meaning there's no real heat transfer that occurs at the tip, which is depending on the design. You get one of two cases where the efficiency can be denoted as 1 over an m times the length over the hyperbolic, or this is a different expression, the hyperbolic tangent of m times L over m times L. This is for a long fin. And this is for a fin with an adiabatic tip. They're just special cases. But, and like, I'm not going to expect you to do a whole lot of calculations associated with fins. The key, what I want you to understand is essentially how they operate in terms of the interplay between the conduction through the fin and the convection that occurs, and how efficiency plays, as well as the factors that govern heat transfer and the efficiency in a fin. This M is simply a grouping of values and constants. Oh, my computer's freaking out. H times P over KAC. And P is the perimeter of the fin. H is the heat transfer coefficient. K is the thermal conductivity of the fin material, and AC is the cross-sectional area of the fin itself, or the slice. There's a couple other expressions that are denoted in the lecture slides. Here's an example. We're not going to go ahead and jump into it, but I just want you to kind of understand that in general, when it comes to fins and fin surfaces, they exist to essentially increase heat transfer, primarily heat dissipation, because it's very rare you're going to see heat going into a fin. It's almost always out. And so this occurs by increasing the surface area to improve convection that occurs off of a surface. And so that's really all I have for steady state conduction. So let's consider switching gears a bit to talk about transient heat conduction. And so what makes transient systems difficult is that not only do we have to consider the temperature gradient with respect to distance or position, but we also have to consider the temperature gradient that exists within the time. And so what that typically means is we have an emergence of differential equations of a second order. And so in lieu of solving second order differentials, we can typically rely on one of several case systems to simplify the expressions and get an idea associated with what we can expect in transient heat conduction. The first special case that we consider is for the case known where lumped system analysis can apply. And so for lumped system analysis, we consider this as a method to approximate transient conduction assuming convection within a system is the limiting factor. And to demonstrate this idea, let's say we've got a ball of aluminum and it's at some T initially. We'll say it's T naught. And the surrounding temperatures, T infinity, and T naught originally is much greater than T infinity. Now, if we consider graphing the temperature of this ball with respect to the position or the radial position center to the surface, and I'll say it's R to make it more consistent. At T equals 0, I can state that the ball will have a uniform temperature. It was brought to a steady state before it was put out into this ambient system. And so what should I expect as I allow this ball to cool in terms of a temperature profile? And so let's see who's the first. Claire, what do you think?
Could you repeat the question?
Yeah, so what kind of temperature profile should we expect at T greater than 0?
I'd expect it to be like a negative linear.
So it should be like this.
Yeah.
Okay. Possibly. Possibly. In general, these kinds of systems will taper, right? Because if I'm looking at the system, I have two forms of heat transfer. I have, my thing will freaking move. I have convection off the surface, and then I have conduction heat transfer that it can exist in the radial direction from the inside of this aluminum ball to the outside. And so depending on the nature of the material, the substance, I can expect over time these temperatures to start falling. It typically follows not necessarily a true linear system unless you're looking at the steady state. It's a little more gradual. And so you can start to kind of see the emergence of what you said. However, what we find is for systems where the limiting factor is convection, instead of having a temperature profile that's a function of position, we can approximate the essentially temperature profile as a single value, which means that as the surface cools, the object and material itself redistributes the heat evenly from the interior to the surface, and such that the temperature, or the mean temperature, is pretty representative of the temperature distribution within the material. And we can expect this to occur for a lot of materials, typically things where the thermal conductivity is high. And we can quantify materials where we can consider dT, dr irrelevant. And so instead, we're primarily simply concerned with dT, dx. And so this is an area where we consider a lump system analysis, because we can essentially consider the entire system having one uniform temperature with respect to time. And we can quantify whether a lump system can occur through application of what is known as the Biot number, where the Biot number is a comparison of the convective heat transfer, or convection, at the surface of an object over the conduction within an object. And so it's a comparison between the two forms of heat transfer that are occurring within the system. Which one is dominating and limiting the system? So I can quantify Biot then as H times L sub C, or a characteristic length, over K, where H is my heat transfer coefficient for convection, L sub C is a characteristic length, and K is my thermal conductivity. So When do we think a lump system can apply? When a Biot number is big or when a Biot number is small? And V, what do you think?
Can you repeat the question?
Yeah, so we can quantify and get an idea of whether we can use a lumped system analysis to approximate our system through the calculation of what's known as this Biot number, which gives us a comparison between the convection at the surface and the conduction within an object. And so if lumped system applies when convection is our limiting factor, do we expect that to coincide with large Biot numbers or small Biot numbers?
I think it's gonna be.
Where convection is the limiting factor.
Right. It's gonna be a small number
Very
that
good.
we divide by the conductivity.
Yes. So we typically say in general, thank you. Lumped system analysis, which I'm just going to approximate as LSA, new government agencies, applies when our Biot number is less than or equal to 0.1. When Biot number is larger than that, that tells us that conduction is going to be small enough within the object that a temperature profile will exist. When Biot numbers are small, that tells us that we can safely neglect the temperature profile and just essentially lump the system as a single temperature value. And so for lump system analysis, we can quantify the temperature, once again, as a respective time, as T minus T infinity over T naught minus T infinity as equal to e to the negative b times time, where T is the object temperature at time T. T naught is the initial temperature. T infinity is the ambient temperature. And B is a group of values, H times the surface area over rho Cp times the volume of this object. Oh, and I realize I never told you what L sub C is. Characteristic length for an object can be determined as V over A sub S, where V is our volume and A sub S is the surface area.
Dr. Lopez, does that apply to any shape?
Yes. So I can rewrite this if I want, if my thing will stop jumping between days, as H over rho Cp L sub C. So any questions on a lumped system analysis, how it can be applied? I'll give you guys a few seconds to look this over one more time, and then we'll look at an example of using lumped system analysis.
Hey, Dr. Lopez, in the B equation, is that a P or a rho?
That is a rho. Very good question. That is density. All right. You guys need a few more seconds to write it down?
Yes.
I understand.
Dr. Lopez,
Yes, sir.
looks like you accidentally erased your e to the negative bt.
Oh, thank you. My notes like to be possessed sometimes. Here, all right, so let's take a look at an example. If it will let me share my PowerPoint, which it doesn't look like it wants to let me. Hold on. Let me try this. Can you guys see the slide?
Yes.
Okay, for some reason it's not letting me share PowerPoint, just as PowerPoint. But anyways, example, we got a dead body. It was found at 5 p.m. in a room maintained at 20 degrees Celsius. If the temperature of the body is measured as 25 degrees Celsius, and the heat transfer coefficient between the air and the body is 8 watts per meter squared Kelvin, estimate the time of death, assuming we can model this person as a 30 centimeter diameter, 1-meter long cylinder. And we can also use thermal properties of that of water for density and heat capacity and thermal conductivity. Where the thermal conductivity of water is, what did I use? 0.617 watts per meter Kelvin. All right, so I'm gonna give you guys some time and breakouts to see how you can do working on this problem.
What did you use as your thermal conductivity of water?
0.617 watts per meter Kelvin.
Okay, thank you.
Of course. All right, I'm opening the room now. Hey, how's it going?
Going good so far. We're using properties of water, correct?
Yeah.
Okay, and we can look up the CP for water.
Yeah, it's 4184 joules per kilogram Kelvin. I wonder if I can chat to everybody, the CP and all that. Can you guys see chat stuff if I send it out all at once?
Yeah, Adam has done it before whenever we were in waiting rooms. He can send stuff like waiting rooms and stuff, and he's done it in breakout.
Well, let me know if you're getting the chats that I'm putting out
Yeah,
now.
that just did. Yeah, I just got that.
Yeah,
and it says it's going to everyone.
Make sure you got all the values you need. I should probably remember to do that. Thank you for that. All right, I'll let you guys keep working.
CP, okay.
How's it going?
Oh, pretty well.
You guys get my chats? Trying to give you guys a bunch of values. I should probably remember to do that for problems.
I didn't see them.
I did not.
Really?
Yeah, no, didn't get any chats.
Is it like the ones that show up at the top of the screen and then they go away?
Interesting. Hold on. Let me try something. I'll be right.
The values are at the top.
Did you guys get that broadcast?
Yeah, it doesn't stay on the screen for very long though.
Weird. I wish it would.
Yeah. You have to like look at it, be looking at it right when it comes up.
No.
So right now we're showing for we just showed for B, we got 0.173, and we're gonna plug that into the big temperature equation to solve for the time.
Dr. Lopez, so CP is 4,184.
Yep, joules per kilogram Kelvin.
Okay. So then that 0.17 value for B is wrong.
Wait, you said CP is what?
4,184.
I thought it was 0.617. Oops.
That's K. K is 0.617.
Oh, okay. I wrote that wrong then.
You're good. I'll give you guys a few minutes. How did it go?
I don't think I'm an engineer today, Dr. Lopez. I think I'm a criminal investigator, really, when it comes down to it.
Okay. You found the body. Was it in electrical? That's the question. It's always in electrical. All right. Joke. So let's take a look at this example. Finding the dead body. We can give him a name if you want.
Orange.
You know what? Orange. I'm not gonna touch that one with a 10-foot pole. All I'm saying is poor Orange over here had a body temperature of 25 degrees C. If we assume when he was alive, his initial temperature was 37. And we know the ambient temperature is 20 degrees C.
Red did it.
Red did it? Okay, it's always red. Red's always sus. Using our lump system analysis equation, T minus T infinity over T naught minus T infinity equals e to the negative bt, where b is h over rho Cp L sub c. Simply plugging in the values will give us an idea of solving for time. Particularly if I take the natural log and divide it by negative t, I find that time is simply the natural log of t minus t infinity over t naught minus t infinity divided by b to the negative natural log. So the first thing I probably want to do is solve for b. And to do that, I'll probably want to know the characteristic length, which is the volume over the surface area. Well, the volume of a cylinder is pi d squared over 4 times L, or pi times 0.3 squared over 4 times 1.7 divided by the area of the two ends, or 2 pi d squared over 4, plus the surface area along the cylinder, which is pi dl. This gives me an L sub c value of approximately 0.069 meters. With that in mind, I can solve for b as h over rho Cp L sub c, or 8 watts per meter squared Kelvin, divided by rho, which is 1,000 kilograms per meter cubed, divided by the C, P 4184 joules per kilogram Kelvin, divided by LC, which is 0.069 meters. Which, if you've solved for your B value, you should have got approximately 2.8 or 2.77 times 10 to the minus 5 inverse seconds. Then, with that, we can solve for time as saying the negative natural log of t minus t infinity, or 25 minus 20, or 5, divided by t naught minus t infinity, or 37 minus 20, which is 17, divided by 2.77 times 10 to the minus 5th inverse seconds, which gives us a value of approximately 44,000 seconds, which we end up as 12.3 hours. And so the time of death was approximately 4:42 a.m. Any questions on that? Hopefully you guys made decent progress on it. I know sometimes it frustrates you that you don't get through an entire problem when we do some breakouts, but it's primarily, unfortunately, due to the fact that we have limitations on time. And if we wanted, we could check to see whether LCA would apply by finding the Biot number, which is H over HLC over K. And if you do that calculation, what you find is the Biot number is unfortunately 0.89, which implies that LCA probably isn't the best thing. And so when LCA doesn't apply, we have to consider one of several other forms of transient heat conduction. One method is through use of what's known as one-dimensional heat transfer approximation. Where if I consider an object or a slab of something, and I have heat transfer occurring from the sides, what we find is through application of symmetry, I can simplify my expressions for heat transfer as a function of both position and time, primarily because I simply have to solve for 1/2 of the system. Because if heat transfer is occurring symmetrically, the other half is essentially the same. And so if I'm looking at something that's being essentially heated from the outside in, I expect, these kinds of profiles to exist over time, right? So I have both temperature as a function of time and as a function of position. If I wanted to write out the derivation, I would get a value that looks a little like this, which states, let's see, negative Ka del T del X dt plus Ka times del T del X plus del T squared over del X squared del X dt equals Ka del squared T del X squared dt dx. Which, simply put, is pretty messy. Nobody really wants to have to do this solution identification. But what we find is that we can approximate the right-hand side, this Ka del T del X squared del X del T, as rho times Cp times A del X dt dt dt, which is meaning essentially that the accumulation of heat that exists within the material will be held within that material as a function of the density and the heat capacity of said material. And so it's a way of converting the heat accumulation into internal energy via the material. And if you want cleaner versions of this, this is page 309 in your text in chapter 10. What I'm getting at is as that heat gets converted into internal energy, we can approximate the partial derivative of temperature as a function of time as a second partial derivative of temperature as a function of position in terms of this grouping of constants, K over rho Cp. And since thermal conductivity, density, and heat capacity are all intrinsic functions, we can define a new property, alpha, which describes the interdependence of these functions as it relates to transient heat transfer, where alpha hold on, my thing stopped sharing because technology likes to be difficult. Is known as our thermal diffusivity. Which describes the ability of a substance to diffuse thermal energy within itself. So, with this in mind, we can solve, and by we, I mean someone else that really likes math, was fortunately able to develop a solution for the cases of one-dimensional heat flow. And what we find is that solution exists as a series solution. So, for example, when looking at a one-dimensional slab, we find that we can approximate the temperature profile, which can be given by Ts minus T over Ts minus Ta, which I'll define in a second, as 4 over pi times the quantity e to the negative A1 times Fo times the sine of pi x over 2s plus 1/3 e to the negative 9 A1 Fo times the sine of 3 pi x over 2s plus 1 over 25, or excuse me, 5 times e to the negative 25 A1 times Fo times the sine of 5 pi x over 2s. And those are the first three terms we really only need for the series solution. And this is where T sub s is the surface temperature of the object. T is the temperature at time t and position x. T sub a is the initial temperature of the object. So A1 is simply a constant, which is pi over 2 squared, S is 1/2 of the object's thickness. And FO is another dimensionless value known as the Fourier number, which is defined as alpha times t over s squared. So I will give you guys a minute to write this down, and then we'll talk about what all this means. It's a Fourier number. If we wanted to define it in words, it exists as a measure of an ability of a material's ability to fuse heat within itself over the material's ability to store the thermal energy. Within itself. I can clean up my writing. So what do we have? We have a really messy series solution that can give us an idea of temperature profiles that exist within objects as a function of both time and position, provided we have some information associated with the temperatures in terms of constant surface temperature and initial temperature, as well as a Fourier number. So if we know time, we can identify Fourier number, and with that and some temperatures, we can solve for T, or essentially the temperature at time T, and vice versa. If we have the temperature at time T, as well as the position, we can solve for the actual time by trying to back out the Fourier number within this expression. And there's a few other expressions that we can look at for sake of time, as well as considering systems associated with directly solving for time for a one-dimensional slab, cylinder, and sphere. And as I showed others, there's equations associated with the temperature profile, the average temperature within the object, which is this T sub B, with this second term on this series solution. And there's also modifications for rectangular and spherical coordinates that are given on page 310 of your text. An easier way to consider this system is through use of graphs such as this one that gives you an idea of, based on the Fourier number, what can we expect in terms of those temperature ratios. And a lot of times it's much better to look at this than having to solve the series solution, right? Because we're engineers, we see math. Beyond a certain point, we'd like, okay, how can we graph it? Even if the graph is ugly, let's use that instead. So with that in mind, we can look at this example that discusses An 8 centimeter thick slab of ceramic, initially held at 90 degrees, is being cooled on both sides by water, which essentially lowers the surface temperature to a constant value of 30 degrees C, assuming the following properties. What is the temperature at the center of the slab and halfway from the surface to the center after 3 minutes? And also, if we can, what's the average temperature of the material after 3 minutes? So go ahead and write some of this stuff down. We'll get started. I'm not sure how far we'll get on this one, but we'll give it a try. Okay, so let's take a look at this one briefly together because we're running low on time. So this is looking at ceramic slab. The thickness was 8 centimeters. The initial temperature was 90 degrees. The surface temperature is 30 degrees. And we're looking for a few temperatures associated with this system, given that the density of the ceramic is 1,025 kilograms per cubic meter. The heat capacity is 800 joules per kilogram Kelvin. And the thermal conductivity is 1.8 watts per meter Kelvin. So we can solve for a few things based off this information right off the bat, that being our thermal diffusivity, which is K over rho Cp, which gives us 1.8 watts per meter Kelvin divided by 1,025 kilograms per cubic meter divided by the heat capacity, which is 800 joules per kilogram Kelvin. We do that, we get a value of approximately 2.14 times 10 to the minus 6th, with the units being meter squared per second. We can solve for our S value, which is 1/2 the thickness, or 0.08 divided by 2, which is 0.04 meters. And our A1 value, which is a constant, which is just pi over 2 squared, is 2.467. And at 3 minutes, since we're looking at the temperature at the center and halfway from the surface after 3 minutes. So when T is 3, or 180 seconds, our Fourier number, which is alpha T over S squared, is 2.14 times 10 to the minus 6 meter squared per second times 180 seconds divided by 0.04 meters squared to give us a dimensionless value of 0.241, which means A1 times Fourier, which exists in that series solution, is 2.467 times 0.241, or 0.594. So to solve for temperature at the center, we use this equation here, this giant series solution, when x equals s, or the center, which gives us Ts minus T over Ts minus Ta equals 0.701, or simply 30 degrees minus the temperature we're solving for over 30 minus 90 equals 0.701, which implies the temperature at the center is approximately 72 degrees. For the temperature halfway, center, we get x equal to 1/2 s. And so if we plug that x in to that long equation, we get Ts over T over Ts over A equal to approximately 0.498, which implies the temperature is about 60 degrees Celsius. Then for that condition, to find the average temperature, knowing that our Fourier number is 0.241, if we'd like, we can use this graph and solve for when our Fourier number is 0.241, which is about here, our average, which is showing here, this TB naught, we get a value of approximately 0.45. So Ts minus TB bar over Ts minus TA is about 0.45. Which implies our Ts bar through algebra, we get a value of approximately 57 degrees. So I skipped a lot of the intensive math on this one, just because it's a lot of writing in terms of that series solution. If you want, we can take a closer look at it in office hours, but I just wanted to give you guys kind of a walkthrough of how to work on this example problem. Are there any last minute questions on it?
How did you find A1?
A1 is just defined as a constant. It's just pi over 2 squared. So
It's
A1 will,
always that.
it's always that, yeah. Why they don't write that in the text, I have no idea. Probably because it's a little neater to write the series solution in terms of a variable. Why do engineers ever do anything? Any other questions?
We didn't use the slab formula.
For this one, we did use the slab formula. It's basically, I skimmed over plugging in everything on the right-hand side. I just kind of told you what the value was. Just because I think that could take 20, 30 minutes, even of itself. All right, so I know I went way over, so I apologize on that, but I wanted to at least get through this without having to backtrack on Thursday. So if that's all, take care, guys. Have a great day. I'll jump over to office hours in about 10 minutes, but As always, if you need anything, feel free to swing by office hours or shoot me an email.
Thank you, Dr. Lopez.
All right, take care, guys.